For this example, we're going to derive the equation that I gave you for the uniform line charge. And this charge is something that runs along the z-axis. And one of the two reasons that I like to highlight this particular example is that, first of all, it's a common situation. It ties together a lot of the concepts that we're talking about in this chapter. But secondly, using this Coulomb's law line integral approach is going to be a painful way to do it. And that will set the stage for when we learn to use Gauss's law. That will set the stage for when we learn to use Gauss's law to solve it and find that it's much easier. You will believe and feel like life is getting better and better as you learn more and more. So let's start with drawing the system. So we have a uniform line charge, rho L, along the z-axis. It runs along minus infinity to infinity of the z-axis. And you want to find the electric field. So this is the z-axis. It runs all the way along. So we'll just draw this out, extends this way. And as we described before, we see that this is cylindrical radially along the z-axis. So that kind of implies that we might want to use the cylindrical coordinate system. Now so we'll march through the steps that I presented previously to work through this problem. So the first step is you want the coordinate system and also to define your source observer vector. So as we mentioned before, cylindrical system, so I'll just write that down, cylindrical coordinate system, and we want to find r. So in this case, let's see. All of our source vectors are going to be running along here. So for a segment here, the location is going to be, r prime is going to be some z coordinate, right? And now let's look at any observer point here. We're going to choose, since this runs up and down infinitely, we can choose any location along the z-axis we want, right? Because if I'm standing here, if I look up, I see infinite charge. If I look down, I see infinite charge. If I take 10 steps this way, I'm going to see the same thing, right? Look up, infinite charge. Look down, infinite charge. So I can really set this anywhere I want. I might as well set it on the xy plane, right, at z equals 0. So if I'm sitting over here, a distance rho away, then my observer vector, my observer location, so this should have a prime here, my observer is going to simply just be rho in the rho direction. So then my source observer vector, which if I'm just looking at generic segment length over here, the electric field will be in this direction. This is going to be my r, and it's going to be equal to r minus r prime. And I already have my expression here. So r is just simply r minus r prime, which is going to be equal to rho hat minus z prime z hat. Right? So that is going to be your capital R vector, and the length is going to be equal to this length, right? So that would be the square root of r squared plus z prime squared. And this is actually a significant chunk of the battle. Like defining these is probably is in many cases the most challenging part. Once you have that, the rest is a little bit more plug and chug. Now, the next step is to find an expression for the charge density and the segments that you'll be integrating. In this case, we'll be doing a line integral because it's a line charge density. So rho L, dl, and dl in this case is in the z direction, right? dz prime. So then step 3 is to set up, and we'll just lump that with step 4, which is to solve it. And then once we're done with that, we're finished, right? Step 5 was to calculate the force if you're given a charge. In this case, we're just looking for the E fields. So this is basically, we're just gonna wrap this all up. The electric field is gonna be we're sticking it at we're sticking with the the z equals 0 coordinate, and we're going to be going all the way around, so we won't worry too much about this, but this is primarily going to be a function of rho, because it's going to look the same. The only thing that's going to be different is how far from that line charge you are. So that integral, it's going to be a line integral, and you can have charge density, this constant, and then we're going to have the r magnitude squared, right? So that's going to be square root of rho squared plus z prime squared, and then times the unit vector, right, which is rho hat minus z prime z hat all over another factor of the square root of rho squared plus z prime squared. And then this is, we're going to add up all these segments, so we're going to integrate it as a function of dz. And the limits of z are minus infinity to infinity. So minus infinity to infinity. With apologies to mathematicians, I really should just be adding a limit. Z, some symbol goes to infinity and putting those there, but what's the point of trying to pretend to be a mathematician when you're an engineer, right? Especially if you can save some ink. All right, moving on. So I feel like being able to set this up is fair game. Okay, the main thing I want to get across is getting to the point where you can set up these R's and line segments and set up the integral. What I'm going to take this the rest of the way, just for us to see how we get that final expression that I presented in the lecture. But for the purposes of exams and evaluations, the next part is a little bit more grunt work that I will not expect you to be able to do on the fly. But definitely the first two steps and getting it to this equation, I think, is fair game for any situation for assessment. Just keep in mind that since in many of these situations, there are only so many that we can reasonably solve without being too ugly. So that also means that in many of your situations, for those of you that are learning this in the classroom, in a classroom setting, the evaluation will largely be assessing your ability to set this up. But let's say we're stuck on a desert island, and the only way we can get off is by finding the actual solution without the aid of any calculators, though we will have an integral table. Let's just continue marching forward. So see, these are two things added together, so we can distribute all of this in. So we're going to have the integral from z prime, well, these should have primes, equals minus infinity to infinity of rho hat dz prime over, we factored this part out, so then we're just left with rho squared plus z prime squared to the 3/2, because we're combining these two. And then we also have another term, z prime goes from minus infinity to infinity of minus z prime z hat, same thing, rho squared plus z prime squared to the 3/2 power. One thing that you can do is you can just say all of this is going to be equal to 0 because this is an odd function. Because of this z prime here that you're actually integrating, it's going to be an odd function, so whatever integral you get on the left-hand side is going to cancel the integral of the right-hand side as you go from minus infinity to 0 and 0 to infinity. So we can ignore this term, and that way we're left with this. So we do some cleanup. We're going to have rho L over 4 pi epsilon naught times, we're going to pull another little trick here. This is going to be an even function, so we can pull out rho is going to be a constant because we're integrating with respect to z. And we're going to change this to 2 times z prime goes from 0 to infinity of 1 over square root rho squared plus z prime squared. or clean up the bottom, should be to the 3/2 power. So we still have our rho squared plus z prime squared to the 3/2 dz prime. And on a desert island, this is kind of as far as we can go without turning to the aid of the integral table that we happen to have brought with us onto the airplane before it crashed. And through our handy dandy integral table, we can find, let me just clean up everything that's outside of the integral first. So if you look this up on an integral table, you'll see that the result is going to look like this: z prime with a rho squared square root rho squared plus z prime squared. And you're going to integrate that, you're going to evaluate that at 0 and infinity. When you put in 0, since this is in the numerator, you're going to get 0. So just evaluating at infinity, you're going to get that this thing is going to be equal to 1 over rho squared, because you're going to have order of z prime here, order of z prime on the bottom. They'll cancel each other out. You're just going to be left with 1 over rho squared. And that will give you your expression for the E field. So this rho squared will cancel out with that. And you are then left with the much cleaner solution that I gave you, that I just threw out elsewhere for an infinite line charge, which is rho L over 2 pi epsilon naught. Remember, because this factor of 2 cancels out with that 4. And then these two cancel each other out, so you're left with one rho term down here in the rho direction. And next time, when we're in the next chapter, when we talk about Gauss's law, we'll find a much easier way to arrive at this solution. But in the meantime, just remember what I mostly want you to pay attention to is that process of setting up this coordinate system, choosing the coordinate system, finding r, and then finding what length segments you're using and setting up the integral.